Alright, so here's another frame problem that I want you to analyze. Again, we have this frame that's pinned at points A and D, and there's these two rods and they're connected to each other through another pinpoint at B. We've got a load acting down on this thing at C, and we're going to neglect the weight of the frame. So there's the general thing, and once again, what we want to do is we want to find the direction in which the pin joint here at point A pushes or pulls on the frame. Now, I'm not asking for quantitative details. I'm not asking for exactly what force that is in pounds or newtons or whatever. I'm not asking the exact direction. I want a qualitative direction. In other words, does it push up? Does it push down? Does it push to the left or to the right, or in one of these other directions that are a combination of up, down, left, and right? You know, which general direction does it push? And what we're going to do, just like the previous problem, is we're going to analyze this thing without any equations. That is, we're not going to set up specific equilibrium equations and solve for unknowns. We're going to use principles of statics and use those to get this qualitative information, whether we're pushing up or down, left or right, or some combination of those. So as before, we're going to start this problem with a free body diagram. So let me label that FBD. As usual, here's my entire frame, and I want to put the forces acting on this entire frame. So I'll start with this load that's acting at point C. I'm going to call that load L. Now moving down to the point A, this is what we're really supposed to find, the direction of that force at point A. You might have a gut feeling for which direction that's in. But again, I don't want you to use that gut feeling. What I want you to do, we're going to use some rigorous analysis to determine this. So let's write this as a general force vector for now. And, well, I guess in general we can write this as acting in some direction like so, but since I'm going to want to split this up just like I did in the previous exercise, I'm going to write this, instead of some general vector acting here, I'm going to write it in terms of its horizontal and vertical components. In other words, I'll say this force acting at point A has a component AX in the I hat direction, and another component I'll call AY, that will be in the J hat direction. Now, what other forces are acting my body? Remember, there's this point B up here. That's where these two rods sort of are pinned together. But in this free body diagram, at B, that's an internal force, because I'm writing this as a free body diagram of the entire frame. And both this rod and this rod are part of that frame. So any forces between those rods, that's inside the system that I'm considering. So it's internal. It's not coming from outside. Pin D, however, pin D is on the outside, so it is pushing or pulling at the end of this rod right here, and we have to figure out which way that goes. Now I can write it in terms of components, AX and AY, just as like I did for point A, and that would be okay, at least for a start. But there's something that we can take advantage of here. And if you recall back to the previous analysis we did for one of these frames, the first one, we noticed that there's something very special about this rod BD. In particular, if we were to draw a free body diagram for this rod BD, just the rod BD and not the other part, then let's look at the forces. We would have one force sort of acting at D in one direction. That's that one. And we have another force acting on B in some direction. Let's call it that way. And these are the only two forces. In other words, this is what's called a two-force member. Remember, again, we're neglecting any weight of the rod. So in order for this rod to be in equilibrium, this force down here has to be exactly equal to that force up there, but in the exact opposite direction. And furthermore, in order for there to be no moment, these two forces have to act through each other. They have to be collinear. Right? That's the only way you can get no moment and exactly canceling forces. In other words, these two forces acting on rod BD have to look something like this, right? Collinear, acting right through each other. Forces have to exactly balance and create no moment whatsoever. So I'm going to call this force down here D. That's the force due to pin joint D on this thing, and then we'll have force up here called B. This is force of pin joint B on this particular rod. Now the force B does appear because B is external to this particular body right here, right? So it has to look like this to be in equilibrium, or alternatively, these two vectors can go inward and point towards each other. We don't know right now, right? It could be one of these or the other ones, but since it's a two-force body, they have to act through each other. That's the important point. So what I'm going to do here on my original free body diagram, at the entire frame, I'm going to put this force acting on point D, or from pin D. I'm going to draw it like so. Again, it is acting through point B right there, something like this. So I'm going to label it D. And once again, maybe this is important on your free body diagram. We don't know the precise direction. We know it's acting through point B, but it could be downward or it could be upward. So it's one of these two, right? Likewise with AX and AY, I'm sort of drawing AX toward the right, but it could be to the left. I'm not sure. And similarly, AY, I'm drawing it upward, but it could be downward. So I'm going to put a little question mark on that one as well, too, at least for now. So that completes the free body diagram of this frame. I've got all the external forces acting on it. All right, so now what we're going to start is what I'm calling the analysis without equations. So we're not going to write mathematical expressions where we're actually going to solve for these unknowns. Instead, what we're going to do is express physical principles for equilibrium and then think through the consequences of those. In particular, I'm going to start off with a moment principle. So let's consider the moment of all these forces about point A. A is the pin joint down here, right? Pin joint down there. And that has to be equal to 0. Again, this looks like an equation, but I'm really just using it to express an idea. We're not going to set up sort of algebraic equations for equilibrium here. This is just the idea that moments about point A have to balance out and add up to 0. And then what I'm going to do is create this table in which I'm going to list all the forces and that the moments that these forces generate about point A, right? So really it's sort of a causal link here. So forces are causing moments. So here we have the individual forces, and again I'm reading them directly off my free body diagram, AX, AY, and the I and J hat components respectively. I got the load pulling straight down. I've got this D that at least right now looks as though it's mostly down a little bit to the left. Right now, what are the moments that these forces create about A? Well, since AX and AY act directly through point A, the point we're taking moments about, we're going to say that these two moments are 0. They have to be 0, right? And then L is acting straight down. We've got a nice long moment arm there, so it's going to create a clockwise moment. So that creates a moment like that. And now let's look at D. D is, as I've drawn it here, D is also acting downward. It has a moment arm. It is also producing a clockwise moment about point A. Now I need, these are the only way I can get moments about A, through these 4 sources, and 2 of them are 0 right here. So we know L produces a moment clockwise. D is the one with a question mark on it. If D is aligned like I have it, then it also is clockwise, and these 2 moments add up to something which is not 0. It can't be 0, right? Clockwise plus clockwise is clockwise, right? Even more clockwise, I should say. So this is wrong, as I've drawn it down here. What we need is for D to create a counterclockwise moment to make this condition for static equilibrium satisfied, right? It needs to go counterclockwise, which means that this direction must go exactly the opposite way. It means that D is not going down and to the left as I've drawn it. Instead, D must be pushing upward and slightly to the right. That's the way that D must go. It must be, in order to create that counterclockwise moment to balance out the load. This is the only way in which this can work. That's a nice little intermediate result. D has to go upward and to the right. Now before we go on, I want to ask a question that's going to be important for us. I want to ask which one of these forces is bigger in magnitude, L or D, right? Here's L right here pushing down, and here's D right there pushing up. Which one is bigger? Pause this video for a moment. Think about it before you come back, all right? I'll wait. To answer this question, I want to think about the moment equation again, right? These 2 forces both create moments in the opposite direction, and these moments must exactly balance each other out, right? So let me just go back up to this picture we have up in the top left. The moment produced by force L, this force up here, has magnitude equal to the actual magnitude of this force times what? It's times this perpendicular distance right here. That's the moment arm. I'll call that DL, if that'll fit in there. Maybe I'll write it down here. DL. Right? It's the magnitude of that load times this length I'm calling DL. There's the moment arm. For the force at D, it's acting right here at point D, producing a force up and to the right. And what is its moment arm? Its moment arm, well, you just extend this rod down, it's this perpendicular distance right there. Right? Can you see that in there? I'll call it DD. There's the moment arm for force D. And what can you say about this moment arm compared to that moment arm, right? This moment arm down here is about half as big as the moment arm up there, right? We have half as much leverage. So therefore, in order for the two moments to balance out, this force D down here must produce a force which is about twice as big as L, right? Because the moment arm is half as big. These two moments have to exactly balance each other out. Since the moment arm for point D is about half as big as that for L, the force of D has to be about twice as big as L. So therefore, we get D, that magnitude, is about twice the magnitude of L, right? Just a little observation there that might come in handy in just a few moments. How's that sound? Does that make sense? All right, so let's go on and continue our analysis. So what we're going to do next is the other equilibrium conditions. Sum up all the forces. That has to add up to 0. Again, I write this as an equation, but really what I'm trying to do is just get its meaning. Add up all the forces, that has to add up to 0. All these forces, add them together, they have to cancel in some way. So instead of taking this and writing down equations of equilibrium, I'm going to construct another table. So in the leftmost column of the table, I'm going to write down my forces again. And these are AX, AY, L, and D, just as we had before. And then in the next column, I'm going to put the horizontal components of these forces, right? We're looking at horizontal. We can take this vector equation and split it into its horizontal component and vertical component. So that's what we're going to do. In fact, we'll start with horizontal and then we'll go to vertical. So AX in particular here, that's all horizontal. So I'll put an arrow there. I'm just looking at the horizontal first. So it's all horizontal. I'll put it right there. AY does not have any horizontal piece. So put a 0 there. L, the load, is straight down. Again, no horizontal piece. And then D it's mostly up and down, but it has a little bit left and right. And we know that D is pushing. We know that we have the direction of D correct now. So we know that it has a component to the right. All right, now those are all my forces. Right, 0, 0, right. And if I take right, add 2 zeros, and add another right to it, this ends up being right. Yeah, but it has to end up being 0. I can't have a net force to the right. So again, I know this one goes to the right. So the AX, that's the one that had the question mark next to it. The AX actually has to go the other way in order to have equilibrium. So I've got this thing wrong again. Wow, another mistake I made on initially. So AX, let's just write this down. It must go the other way for equilibrium. So it must go to the left. And therefore, on my free body diagram, let me just erase this question mark, erase that arrow there. On my free body diagram, let me draw it correctly. This force has to be going to the left. Right? To the left. That's exactly the way it must go. Cool. Now let's go to the vertical pieces. In the vertical direction, AX has 0 contribution. AY, what's it doing? Well, as I've drawn it, it looks as though it's going upward. So let me draw it upward, at least now, tentatively, with a question mark there, perhaps. And L, that's down, like so. And D again is upward and to the right. We know the direction of D. We already got the part that's to the right, and then it also has to have a part that's upward. Ooh, interesting. So I know L is down, I know D is up. So in principle, I can at least, just looking at this qualitatively, it looks as though I can get these two to balance out with just L and D alone, and I don't need an AY. So does that mean AY is 0? No, it doesn't. If these two exactly canceled out, then AY would be 0, but do they exactly cancel out? Remember what we said earlier. We said that D was about twice as big as L. And look at D. Almost all of it is in the vertical direction, right? There's a little bit of it to the right, but almost all of it is in the vertical direction. Let me just draw a quick vector triangle for D here. D is upward and to the right. It has a little piece that goes to the right, but most of it is going upward. So if D is about twice as big as L, then this fraction going upward, this has to be bigger than L. Since this part from D is big going up, is bigger than the part of L going down, that means I need more force down in order to get this right, in order to get this all to cancel each other out. So therefore, again, I got the arrows wrong here. We need this vector, the AY, to point down in order to make this vector addition work, right? It's the D that's the big one. L is smaller than D, so it doesn't quite completely compensate for the D going up. So I need more force going down. That comes from the AY. AY is going to have to push down in order to keep this system in equilibrium. So I'm going to come back here. I'm going to erase that direction here. AY has to be pulling down. It has to go that way in order for this thing to be in equilibrium. And hence we're essentially done, right? So this is telling us that this force at the pin joint at A here, it has a piece downward and a piece leftward. So I'm saying down and to the left, and that's my final answer.